I think everybody's got the idea that the speed of light is pretty fast. So how do you go about measuring it? Galileo had a great idea. Put a lantern on top of one mountain, miles away, put a lantern on top of another mountain. You have them covered up. Somebody standing on this mountain uncovers their lantern. The light shines to this mountain. As soon as they see it, they uncover their lantern. The light comes back. And the first guy on this mountain measures the time. It didn't work. Human reaction time is just too long for this. Well, back around the same time, there was a Danish astronomer named Rømer. He had been plotting the motion of the Earth around the sun, Jupiter's motion, and one of Jupiter's moons. Now, Jupiter's moons go behind Jupiter, and they would all of a sudden disappear from view from Earth. Then they'll pop out on the other side. He's observing this motion while the Earth is going around the sun. It takes a long time for Jupiter to move, so we'll just pretend it didn't go anywhere, and the Earth goes all the way around over to here. The predicted motion of the moon of Jupiter going around and around seems to be thrown off by that extra distance. Then when the Earth moves back to this position, everything's back the way it was before. So the timing is being affected by this distance. Rømer figured out that it's due to the speed of light. He estimated the delay in the period of the moon to be about 22 minutes due to this distance of about 3 times 10 to the 11th meters. That's about 2.3 times 10 to the 8th meters per second. Not bad, considering this was done in the 1600s. Well, in the 1800s, 2 French physicists were working on measuring the speed of light, Fizeau and Foucault. You might be familiar with that name due to the pendulum that's in the Franklin Institute and elsewhere around the world that indicates the Earth's rotation. There were different versions of the experiment, but it eventually led to a rotating octagonal mirror. This experiment was performed by the American physicist Albert Michelson in the late 1800s. This required a beam of light to shine onto the mirror. It reflects off, going down this way. It continues on for 22 miles, striking another mirror. Reflecting off another mirror and then back to the original mirror, it comes all the way back to the rotating octagonal mirror and reflects off into an eyepiece where we can see the light. So he needed to get the time for this to occur. He did it by controlling the speed of the rotating mirror. When the mirror rotates into this position, the beam of light is reflected down the track. It's going to come back. But where will this mirror be? This one will have rotated out of the way by the time the light comes all the way back. Well, it's got to rotate enough to get the next mirror into position for this to occur, or the beam is going to be deflected someplace else. So you know that the time it takes to go down and back is the same time for this mirror to rotate over. That's 1/8 of a rotation. If it rotates too fast, the beam will be deflected over here. If it doesn't rotate fast enough, it'll be deflected this way. So only when it rotates at the exact amount will it go straight up. Well, that mirror is about 35.4 kilometers away. You have to double that distance. Well, this occurred when the mirror was rotating at about 3,326 radians per second. Using 2 pi over the period, we get a period of about 1.89 times 10 to the minus 3 seconds. And that's the time for a complete rotation. We only need 1/8 of that time. So that's 2.36 times 10 to the minus 4th seconds. And that's the time it takes for the light to go down and back. And that gives 3 times 10 to the 8th meters per second. And that is one of the most accurate measures of the speed of light. How about one more method? Microwaves resonating in a cavity. What's that? It's standing wave patterns in a microwave oven. Microwaves are a form of electromagnetic radiation, and they'll travel at the speed of light. Inside your microwave oven, they form standing wave patterns. Well, I put a chocolate bar in the microwave oven without the device that makes it rotate, and the standing wave pattern where there's an antinode is where it gets hot. So you watch where the chocolate melts at these hot spots, and you measure the wavelength with a meter stick. Well, ideally, we should get about 12 centimeters for this wavelength. In my experiment, the first trial may have actually been about that. In the second trial, it was definitely off, and it was a blob, and it was hard to tell. That may be due to the type of microwave oven and the way the waves get reflected inside. If you leave the chocolate in there too long, the blobs just start to get hot and they spread around, and you're not going to be able to tell. So how do we find out what the speed of light is? Frequency times wavelength. The microwave operates at about 2,450 megahertz. Plug in the data. Hey, you get about 3 times 10 to the 8th meters per second. Just as an aside, how does a microwave oven heat your food? It's all about the water molecule. When the electric field is directed this way, the water molecule wants to flip around. Now the water molecule is facing this way, and the electric field has reversed. This causes the water molecule to flip back and forth, and that causes a lot of agitation, heating up the food. The water molecule has a certain amount of rotational inertia. It has a certain amount of charge distribution, and this frequency is tuned to the resonant frequency that the water molecule will rotate at. So it's a resonance. It's a resonance with water molecules. That's why the food gets hot and the ceramic plates don't. There's no water in the ceramic plates. Now think about this. Why don't you get cooked? You're standing outside the microwave oven looking through the window. Why don't those microwaves just go right through the glass and hit you? The glass has a wire mesh. I'm sure you've noticed that. The microwaves can't escape because the holes are too small for such a long wave. But visible light is a very short wave, and those holes appear very large, and they come through so you can see your food cooking, but the microwaves can't escape through those very tiny holes. So what problems might we have dealing with the speed of light? We could clap blocks and measure the speed of sound because the speed of light is so much greater than that sound. But what about the speed of light over greater distances? Might we see a delay caused by the speed of light? If you're on the surface of the earth and you want to talk to somebody over here, the radio waves from a phone communication system can't go directly here. They might have to be bounced off a satellite. If the satellite is in geosynchronous orbit, it's going to be about 3.5 times 10 to the 7th meters away. So how long will it take for a radio wave to transmit to the satellite and then back down to the other person? You have to double that distance. You're going to get about 0.23 seconds. So if I say hello, how long do I have to wait to get a reply? Another 0.23 seconds. Well, look, that's noticeable. And that's what you notice when you see reporters on television talking to a correspondent on the other side of the world. You hear them ask the question, and then there seems to be a delay. They're just standing there. Yeah, they're waiting for the signals to go back and forth. There's a delay because they haven't heard the question yet. And then when they respond, we still have to wait for that to come back. The delay to talk to an astronaut on the moon and then get a response, 2.5 seconds. How about the time delay to communicate with a robot on Mars? You want to send a signal to Mars, have it take a picture of something and send it back. What's that delay going to be? When the Earth is close to Mars, it might be about 3.2 times 10 to the 10th meters. So go figure out how long it's going to take now using the speed of light. It's about 4 minutes. But if the Earth is on the other side of the sun and Mars is over here, it's about 8 minutes just to go this distance. To go here, another 8 minutes. So that means it's 16 minutes plus 4 plus 16 again. Now you're talking 36 minutes to send a signal and then to get a response back. Well, someday maybe we'll send a satellite out to Proxima Centauri, the closest star to the Earth besides the sun. How far away is this thing? 4 times 10 to the 16th meters. How long would you have to wait? Send a signal to the satellite and have it come back. Don't forget to double the distance. You're going to have to wait 2.7 times 10 to the 8th seconds. You realize that's like 8.5 years? We're never going to be able to communicate well with any satellites that are going that far away. This is how come everything has to run autonomously for these satellites that get far away. Even the delay to Mars is great enough for the robots on Mars to have to run autonomously. They have to respond to conditions as they happen, and they can't rely on a remote control unit from the Earth. So we can say that the distance from the Earth to this star is 4¼ light years. Now that's a times there. That's light, speed of light, times time. Speed of light is distance per time. So the speed of light times time is the distance. If that time is 1 year, then that's the distance light will travel in 1 year. That is a light year. We have about 3.15 times 10 to the 7th seconds in 1 year. That's about 9.5 times 10 to the 15th meters, which is so big that we just work with light years. It's much more practical. Well, you got plenty of problems and more reading to do in the chapter notes. Have fun.